Hi, everyone. My name is Chenggang. I'm a co-founder and CTO of Aqueduct. So you can find here in the upper right corner is a link to our GitHub repo, open source GitHub repo. So I think it's actually been 4 years since I gave an in-person talk. So I'm super excited to be here. Today I'm going to talk about large language model for the rest of us, right? So why the rest of us? Because up until very recently, right, these foundational models are sort of exclusively owned by tech giants like OpenAI and Google. But now, as we saw, right, both industry leaders and academic institutions are sort of releasing these powerful models and making them publicly available, which allows the rest of us, right, to potentially take advantage of these models to generate values for our own business. So today, just a brief agenda, right? We are going to go over the recent advancements of foundation models and talk about the new challenges and discuss opportunities as well to run these powerful models, especially in the cloud. And also, I'm going to tell you what Aqueduct is and how do we run a Llama pipeline with Aqueduct. And finally, we'll go over the technology behind the curtain, right? What's all of these cool technologies that enables you to easily run machine learning on your cloud. So, the advancements of foundational models like GPT and BART are happening so quickly, right? And there are some companies you've heard of, and maybe about 1 million you've never heard of. And in fact, since I started this sentence, right, maybe 10 new generative AI startups have just incorporated. But the most crucial question we need to answer is, how can we generate business value with these models, right? So letting ChatGPT sort of write sci-fi novels are cool, but that's not really business value, right? On the flip side, plugins like GitHub Copilot, right, is doing actually an amazing job in bringing value for software engineers like us. So I've actually been a big fan of Copilot, using it every day, and now I think it's essentially doubling my productivity. And this really the critical question, right, is the critical unlock for business to benefit from foundation models is to be able to use them with proprietary data. But just wait a second, right? Things are not quite that simple because with this hosted model APIs, you have to consider a number of difficult issues. For example, they're too expensive to run, right? Requiring beefy, multi-GPU cluster to generate high-quality predictions. And maybe there's potential IP issues, right? If GPT is answering my business questions, does the copyright belongs to OpenAI or Google or my company? We don't really know that. And due to these hidden architectures, debugging becomes extremely difficult. And we have proprietary APIs that ties our applications to a single vendor, right? So obviously there is this lock-in issues. And finally, we may have data privacy concerns because we're essentially sending production data to companies like OpenAI and Google and so on. But as software engineers, right, we actually had solution to all of these problems for a few decades now, right? It's called open source. And the good news is, even over the last month or so, right, we've just seen an explosion of this high-quality open-source foundation models released by industry leaders like Meta and also academic research labs. So I'm sure you've heard of Meta's Llama model, and then comes Databricks' Dolly. There's also this Stanford's Alpaca, which is basically a fine-tuned version of Llama with 7 billion parameters. And most recently, right, as our previous speaker also alluded to, there is this Vicuna model released by Berkeley. Actually, one of our co-founders and VP of product, Joey Gonzalez, was heavily involved in this work. So it achieves 90% of ChatGPT's quality with much less compute resources. Basically, these models can get us pretty far, right? Maybe not 100% of the way they are, but asymptotically getting closer and closer to the quality of hosted models. And this open source movement, right, unlocks significant advantages. No more ballooning costs because smaller models are more capable of just running on a single Mac is sufficient, right? You don't need multi-GPU clusters. And similarly, no longer have vendor lock-in concerns and IP concerns and whatnot. Data privacy regulations fully gone because models are self-hosted, fully in your cloud. And the last point, right, it's easier to debug because you have the full open source, source code here. Also gives you opportunity to fine tune, right, for specific results with full context. So I think this last point of fine-tuning is actually pretty important because to generate business values, right, you need to integrate LLM into your existing workflow, right? For any business, right, your unique asset, right, this durable moat is your data. And we believe this last mile of retraining and fine-tuning foundation models with your own data is actually going to be, the core differentiator that sets you apart amongst your competitors. So open source foundation models are great, right? And I wish I can simply just run pip install LLM and LLM.generate for it to answer my business questions. But as we all know, right, unfortunately, things aren't quite this simple in reality. So running machine learning, right, even maybe just a scikit-learn model in the cloud turns out to be pretty hard. And I'm showing this, but don't get me wrong, right? All these cloud infrastructures here, Ray, Spark, Kubernetes, they're super powerful. But usually in your MLOps, the entire stack, right? Maybe as Robert said, very well put, right, in his intro talk, there is just no one-size-fits-all solution here. Your workflow, may involve some data systems like Snowflake. We want to do some batch processing using Spark and distributed training using Ray, and so on and so forth. So each of them, right, have this unique set of APIs, and any attempt to put them together, hooking up all the wires, is going to be a nightmare. So you probably already know about this, but we've heard this over and over again, talking to hundreds of users. MLOps is just a knot of different systems and services. So adding foundational models, right, to this MLOps knot further complicates the picture because now managing LLM environments requires yet more libraries and yet more infrastructure and more specialized hardware. And once you get past this setup phase, right, then there comes actually a million other concerns, unfortunately. And here are some of the examples of the most common ones that we've heard of. The first one being the runaway cost, right? We all know GPUs are expensive, so you don't want to over-provision these resources when you don't need them, right? So your underlying infrastructure needs to be able to detect your workload volume and dynamically sort of adjust the cluster sizes to be cost efficient, which means scaling up the cluster size when there's demand and scaling down the cluster ideally to zero node, right? When the cluster remains idle. And then another concern is this lack of resource availability, right? GPU is a scarce resource in the cloud, and you can't simply make the assumption that whenever you need it, it will be available to you. So maybe at the time of your request, right, it's available in one region but not the other. So your system, in order for these foundational models to reliably generate predictions, you need to have some of the robust failover mechanisms. And the third one that we've heard of is this poor visibility, right? Each cloud infrastructure has these bespoke APIs to surface all the log. So when things fail, it becomes extremely difficult to connect all the pieces, all the dots together to diagnose what's really going wrong. And also, even when things are succeeding, it's hard to know how our pipeline artifacts are evolving over time to detect this potential data and model drift. So, tools that address all these concerns either, currently don't exist or are extremely complicated to set up and use. So essentially, these challenges, right, means you need to be an expert both in the machine learning space and in cloud infrastructure to run any serious machine learning in the cloud today, and even more so for foundation models. Taking a step back, right, we've actually been thinking about these problems for decades. I did my PhD at the Rice Lab with the great folks from Anyscale who also graduated from Rice Lab. We're essentially literally sitting in the same office space at that time. And my time at the Rice Lab, along with my co-founders, we worked on scalable cloud infrastructure, right? Like auto-scaling cloud storage systems, the first stateful, function as a service, serverless computing engine, and a ton of, this original work on prediction serving systems and performance optimization techniques. And what we learned, right, is that not only is the cloud infrastructure hard and has a lot of interesting research questions, and also, there's this big problem of developer experience, right? And this becomes super clear to us when one of our co-founders, Joey Gonzalez, started teaching this Berkeley data science curriculum, right? So the students attending this class, they're not computer scientists, right? They're domain expert in maybe chemistry and economists and so on and so forth. They are writing machine learning code that needs to access cloud, but they're not trained to operate this complicated cloud infrastructure. Which leads us very naturally, right, to this question or mission of how can we make their lives easier, right? And that's exactly the goal of building Aqueduct, a fully open source control center for AI and ML in the cloud. More concretely, as you see here, right, above Aqueduct, we have your favorite machine libraries like MLflow, scikit-learn, and maybe Great Expectations, and weights and biases, and so on and so forth. And Aqueduct sort of allows you to keep using these libraries that we all know and love and offer a seamless developer experience to build great ML models. And then when running these models, right, Aqueduct acts as a single interface to run machine learning on your existing infrastructure, like Spark, like Ray, right, like Kubernetes, what have you. So essentially, here, we aren't really building a better component for any of the existing stages in the lifecycle, but instead, we're building this unifying ML-centric APIs that integrate with and empower industry-standard components. So I've talked enough about the high levels. Let me show you exactly how it looks, right? So here we have just a stylized example of how you might train and validate a machine learning model. And you can imagine writing code like this on your laptop. But as soon as you write this pipeline, right, you will want to run it in the cloud, right? And Aqueduct makes it turnkey. So let's say we may want to run this train function in a Kubernetes cluster with a GPU, right? And the validate function in a serverless framework like AWS Lambda. So with Aqueduct, all you need to do is decorating your function like this. So we use the op decorator for the train function to basically, we indicate we want it to run in our AWS CKS cluster, and that this operator requires 1 GPU resources. And similarly, for validate function, we specify the engine to be our Lambda service. And you can imagine having similar function that runs on Ray and Databricks and so on and so forth. So yeah, with just a couple line of decorator code, the training pipeline is now up running in the cloud using actually multiple cloud infrastructures. All right, so now that we know the sort of the basics, right, let's jump into a demo which shows an end-to-end pipeline built with Aqueduct that uses the Llama model. Right? Maybe just to remind you a little bit about what Llama does, right? So at the high level, it's a foundation model that does sentence completion, right? So given a sequence of string tokens, it sort of tries to understand what's going on and generate the next few tokens that makes the most sense. So let me stop sharing the slide and share my Jupyter notebook. So just 1 second. All right. Okay. So we have this pipeline in the notebook that basically does sentiment analysis on hotel reviews, right? We actually built this earlier, and you can find it in our repo. All that's happening is we're extracting some data from the Snowflake warehouse and using this transformer package to just generate some sentiment scores and a positive or negative label and attaching them to the original table. So in this demo, we will actually augment this existing pipeline by using Llama to auto-generate customer service responses. So let me just quickly go through some of the basics, existing pipeline setup, so you guys have some context. I'm not going to go through all the bits of details, but if you guys have any questions, feel free to ask in the end. So obviously, we want to import Aqueduct and set up the client and all that. And using Aqueduct, we're going to just get a connection to our Snowflake warehouse and start issuing SQL queries. So basically, once you get the Snowflake, you can use our .SQL API and write arbitrary SQL query against this warehouse. So you don't have to touch this low-level Snowflake APIs and whatnot. In this case, we're just interested in the full hotel review table. So the query is just select star from hotel reviews. The return object we get is simply a wrapper around a pandas data frame, and we can inspect the content via this get API. So now here we can see our full table here with 100 rows, and this review column is what we are interested in for this demo. And these steps are just running the transformer, running the sentiment prediction model from the transformer package that I briefly discussed. Basically, all this is doing is importing the transformers model and then running the model against the reviews, generating that two column and appending it to the original table. Zoom in. Does this look a little bit better? More? Less? That's good. Couple more. This? Too big? Okay. Yeah. Sorry. Does it show the whole thing, actually? I think so. Yeah, good. All right. And similarly, we can invoke the get API to see the table content, and we saw these two columns being appended. So before we jump into Llama, right, note that it does require a GPU to be performant. So let's maybe run this operator with a GPU node inside of a Kubernetes cluster. So we talked about, Aqueduct is focusing on enabling you to run machine learning on your existing cloud infrastructure. But as we also talked about, right, managing these resources in your cloud is actually a huge pain, and nobody really wants to deal with this kind of chore. So we actually give you the capability of having a full serverless experience by managing these resources like a Kubernetes cluster on your behalf. So here, right, you can let Aqueduct create an on-demand auto-scaling EKS cluster just by doing this. And then, once we connect to this integration, we can inspect the status, and we saw it's active. And then we can just use this engine in our Llama operator. So basically, here's the interesting part, right? I'm going to show you how do we integrate Llama into this existing pipeline with a single line of code. Basically, in addition to specifying this engine, right, all we need to do is specify aqueduct.llm.llama as our requirement. And then we can import the package and use it to do batch inference. So what's happening inside of this function, right, is in order for Llama to generate meaningful, a slightly higher quality result, I'm going to just do a little bit of a prompt engineering. So basically, for the first two lines, what's going on is for each review, I'm appending what I'm calling a guide. So basically, after each review, I'm saying, given this hotel review above, the customer support should do the following, right? So after I finish with the prompt engineering, I'm just going to import llama.generate, and feed it with this prompt for it to generate the rest of the sentences. And then the rest of this example is just doing some post-processing. This line is basically extracting out the content that after this guide token. So that's the real Llama response, right? And I'm turning this into a pandas series of a column called response and appending it to the original table and returning back to us. So let me also execute them. It's actually saying it makes use of this on-demand cluster, and the cluster is active, so we're ready to go. So basically, what's happening under the hood, right? We're running this operator with an AWS instance with a GPU, the Tesla V100 instance. In this case, it's running the 7 billion parameter version of Llama, and we pre-configured the batch size to be 8. So this data set is 100 rows, so we roughly expect the iteration takes maybe 12 to 13 iterations to finish the computation. So the whole process, I think I pre-run this multiple times. It takes approximately 2 and 2.5 minutes. So while this is still going, let me show you the rest, right? So after maybe we get this sentiment table with Llama, another thing we can do is to attach a metrics that maybe compute the average number of tokens generated by the Llama model, right? So all we need to do is similarly, we input the table and we just do some simple Python like pandas transformation and get the token count and returning the mean value. So here I also execute this, and let's construct the full pipeline. And we have extracted our data from Snowflake, and we can also save our data back into Snowflake via the snowflake.save API. And then finally, we can just publish this pipeline into the cloud. While it's still executing, I actually pre-registered the workflow, so I can show you guys how it looks like on the Aqueduct UI. If we click into the Workflows tab, you can see our demo customer sentiment with Llama pipeline. And it actually shows our metrics as well. It's the previous computation gave us the average number of token is 35.57. When we click into this, we can show the structure of our workflow, right? From the very beginning Snowflake query that we put here to all of the intermediate artifacts being generated. So the interesting part, right, if we zoom in to this operator, right, is this generated response operator that make use of Llama. You can see this icon is actually indicating that it's running on top of Kubernetes, right? And then we also get the full context of our source code and our engine and requirements. So whatever configuration we put there are fully honored. And then the most interesting part, maybe let's look at the results being generated, right? So let me actually enlarge this a little so you can see the full table. See here, in addition to this review, label, and score, we actually have this response. Right? Let's see how Llama does on this workload. So given this damaged bathroom shower screen, blah, blah, it's generating something like, we need to assess the damage and contact insurer for the quote, agree on the quote, and authorize the work to be done, and take photos of damage, and so on and so forth. And maybe let's look at another example. Let's say if the reviews are very positive, it says no negative, right? So it's actually responding with, thank you for providing feedback, and we appreciate you taking the time to complete the survey, and hope you have a good time. Right? Questions?
Is it fine-tuned, or is it just somehow
the only thing I fine-tune is the batch size, because I need it to fit into one, an instance that have only one GPU, but I didn't fine-tune any other parameters in this case. Yep.
Just original weights?
Original weights, right? Unmodified. Yep. Yeah. So as you just said, right? It's running a 7 billion most smallest Llama model. So don't expect the quality to be super high, but it's getting somewhere. Maybe the last thing that I wanted to show you guys is this API, right? So this is absolutely an alpha feature that we've been rolling out, and we've been continually to iterate on this API design. So currently, if you need access to any foundation models, all you need to do is to put this line here, and you can imagine adding more support to Vicuna and Alpaca and things like that in the future. But another thing we're considering, right, is as your workflows and demand becomes more and more complicated, we definitely want to allow you, giving you flexibility to pass in your fine-tuning and custom parameters into these models, right? So the philosophy that we wanted to embrace, right, is to have this sensible default where if you just want to try out stuff, this single line is sufficient. But if you have, custom requirement, maybe you want larger batch sizes because you have beefier compute, we want to also expose this configuration for you so that you can pass it in and then let Aqueduct spins up the right service for you. Okay. So that wraps up the demo. Let's get back to the slides. Give me 1 second. Okay. All right. Just to recap a few important takeaways, right? So Aqueduct support accessing large language models and in a few lines of vanilla Python code. It seamlessly integrate with and can even manage, right, your cloud infrastructure. And we're fully open source, so the features we're building are driven by community feedback, right? So if you have any thoughts on what you want to see next, we love to hear from you. Of course, there's a lot going on under the hood to make all of these features happen, right? So let me just give you a very brief overview of the technologies behind the curtain. The first step is obviously what we call compilation step, right? The Aqueduct takes in your decorated function and generate a job spec that the target engine can understand. Right? This could be Airflow job spec, Ray task graph, and Kubernetes job spec, and so on and so forth. And we also assemble the environment to run these operators, right? So this could be, transpiling an Airflow DAG, packaging Python environment to be run on the Spark EMR cluster, or as you just saw in the demo, right, setting up this foundational model environment so you can access them with a single line of code. And then we enter this optimization phase where we use the various system-specific techniques to improve performance. So here are a few of them in flight. So for operator fusion, that basically means separate stages of the workflow may pass significant data, right, like videos or images. To minimize communication, right, it can be very beneficial to fuse these operators to avoid data transmission. Another optimization is what we call this locality-aware scheduling. So while prediction pipelines are typically computationally intensive, there can also be significant data exchanges, right, as we just discussed. And remote data access can easily become a bottleneck unless we take advantage of the locality by putting computation near the cached data. And there's a few others like competitive executions and more technologies that I won't go into details. But if you're interested in, happy to talk more offline. And finally, the last step is, Aqueduct operator inspect our optimized execution graph and analyze these operator dependencies and launch them to the cloud. And data exchange between operators are completely abstracted away from you. So we pick the optimal serialization scheme for each common data types and automatically sort of transmit them across operators. And we're open source, right? So if you have custom data types and custom serializations, you can also contribute to our open source as well. And finally, we persist all the intermediate artifacts, right, generated by this pipeline step into the storage system of your choice. So, and we also version them and keep all the snapshots so you can analyze how your data and model are evolving over time. Okay, so let me just conclude with this slide. If you're interested in the ideas and the directions that we're headed, please give Aqueduct a try. Here's this another, again, big QR code that leads to our GitHub repo. So give us a star, if you enjoyed the talk and the demo, and happy to take questions.
If you can quack, you can be part of Aqueduct. Okay, so I guess one of your first slides was sort of like showing these like ML tools sitting on top of Aqueduct, and I think from the demo it felt more of like sort of like job distribution as the sort of like core functionality of Aqueduct. So I'm a little bit unclear on sort of like where things like WB fit in, especially since WB has launched, which is kind of similar, it seems. But my main question really is like, where's the configuration for these destinations that you're shipping these jobs off to? I don't think we saw that, and maybe I missed it, but that was my main question.
Right. So the question is maybe if we look at the code snippet, it's about for these custom engines that our operators are going to be launched, in most cases, you need to specify some custom configurations together with that, right? The environment parameters and stuff like that. So this is obviously a simplified example, but to specify your custom parameters for example, Kubernetes engines and some others, it's also part of the decorator specification, right? So in addition to this engine, you can specify, maybe which Docker image that you want it to run on if you have custom Docker images, and maybe the pod affinity and tags and stuff. We don't have like all of the features I just described, but this definitely work in progress here.
I guess I'm wondering like where you do that work. Like, is there a Terraform that you're also building to set up these resources in addition to this, or that's part of this.
Yeah, so Terraform is more of maybe a script that on your side to create those infrastructures, but to run this job, right? It's more of a pod level or application parameters. So in this case, you can simply pass it into the decorator, and there is no need for neither us or your end to manage Terraform like Terraform script in this. Yeah. And so for the maybe if you're referring to this on-demand cluster that you're referring to, we are actually using Terraform to dynamically spin up and down the cluster for you. Right? So that does require Terraform script.
So we got a question.
Just trying to understand the scope of this product. Like, you talked about inference deployment to cloud, not training. You talked a bit. Can you hear me well?
Yeah, could you maybe repeat the first part?
Yeah. the scope of Aqueduct, like what all are the capabilities of this open source product? Like, can I use it for training? Can I use it only for inference and scaling?
Right.
Like, how is it different from something like PyTorch Lightning and Determined AI's product for deep learning trading?
Yep. So the question is, what's the real capability of Aqueduct? Is it limited to training, inference, and whatnot? So I think the answer to that is basically our. Let me show you this. This architecture here, right? So the main goal of Aqueduct is integrate with your existing cloud infrastructure, right? So the example I gave, I believe, is if your underlying cloud infrastructure you're already using Spark for batch processing, Ray for distributed training, and maybe MLflow for experiment tracking. Right? Aqueduct allows you to integrate any of these existing cloud infrastructures. Right? So whatever cloud infrastructure you have, that's the capability that Aqueduct can offer. So it's more of offering you a turnkey way to program these infrastructure, right, at the Python level. Just on your laptop, decorate a few functions and launch them to different cloud, and that's all you need to do. So, does that answer your question?
Yeah, still, for example, let's say I want to use it as a feature store, enterprise class feature store.
Yeah.
Can I use it?
So we don't have feature store resource integration yet, but we're actively working on implementing integration with Tecton and Feast. So in this case, it's more of so maybe the feature store, you can treat it analogously as our data integration, right? I've shown an example of how do we connect to Snowflake, right? You use aqueduct.snowflake.sql and you issue arbitrary SQL query. And once you register connection with Tecton and Feast, you can do similar stuff, right? Like maybe tecton.get your feature. And all in your Jupyter notebook, you can access data warehouse feature stores, run things on your existing cloud infrastructure, all in one place. Yeah.
Are you also working on probably supporting other hardware engines and libraries built by NVIDIA, like their Tacotron for distributed scalable large model training and stuff, and inferencing? Also have a product for inferencing as well.
Right. Great question. So currently, we're fully focusing on the open source effort. So we're not investing a lot of engineering cycle to building our own execution engine. Right? But as any of this existing framework, right, maybe Ray and Spark implemented support for that, and you can basically integrate that Aqueduct with these engines and use them. Right? And maybe in the future, if we decide to implement our own engine, our hosted service, we will definitely consider working with this powerful hardware resources.
There's one more question over here, but I just wanted to add something to what you mentioned, that how does the individual workloads fit in with, say, Aqueduct? And correct me if I'm wrong, if you're using Ray and you wanted to use the feature store, you can actually use it because we have integration with Feast. Right? So if Aqueduct is using actually Ray to orchestrate its task or workload, and within the Ray task, you want to talk to the Feast feature store, you can actually do that, right, within Ray.
Yeah, that's also a possibility.
Is there any other open source platform that falls on the same lines, or is it like something really novel and exclusive?
It's a great question.
He's asking, can you put any other logo up there?
Yeah. Let's see. So it's a good question. We've heard of maybe there's this open source library called. Let me actually check.
The best analogy is probably Kubeflow that folks have heard of. Kubeflow does many similar things, but also exposes a lot more Kubernetes-ness, which, depending on your perspective, can either be a good thing or a fantastic.
Yeah.
All the previous questions that I've asked kind of lets me know exactly how is it different from Kubeflow, so I would not worry about that.
Yeah.
But I just wanted to hear your perspective on if you think there's anything that comes close, because you seem to be working very synchronously with academia, and all the integrations are possible somehow. So it looks like you have already explored the possibilities of integrations and what already exists there.
Yeah, in academia, back during our PhD days, we've been just heavily focusing on the cloud infrastructure, like scalability and performance side of the things. But this new direction, right? I think what we realize, right, what's really important. These technologies are not very meaningful without the people using it, right? So this new abstraction, how do we program the cloud? How do we make it as turnkey as possible to use this by integrating with all of these existing technologies, including the one that we built back in our days at Berkeley, right? Are this new focus? So.
We have any questions?
I realized I was also uncertain about auth in your notebook environment. Like, how are you authing? Or do you have to be in the same VPC? Like, what? Yeah. Can you talk a little bit about authentication for having access to these resources?
Right. So it's basically, so first of all, it's fully open source, right? So there's no sort of security concern of having your data shipping into third-party APIs and stuff like that. But like maybe just to give you an example, if say you want to run your wait a second, let me pull up the notebook. To run your compute, right, in the AWS cloud system, what you can do is just provide your cloud credentials and specify the regions and also maybe the credential file path, right? So whatever account you give us, we have the permission that's restricted to that account to launch compute for you, right? So
This is all local. This dashboard is all running.
yeah, so it can be run from anywhere. Currently, it's just running on my laptop, but it could be on an EC2 instance, on a Kubernetes pod, and yeah, anywhere.